Oh, great. All right. Welcome back to another lecture. Today we're going to talk about determinants and matrix inverses, and the title of today's lecture is "Extracting Insight from Data." Okay, so before we start, I'm going to have you pause the video and basically answer these three questions. So, when unexpected stress arises, I feel overwhelmed. So, read these three questions and then write your answer between 0 to 5 and then put them in a vector, right? 1 2 1, like that. Okay, and then we'll save it. We'll get to it later. Okay, so once you answer that, let's talk about sizes. Previously we talked about how to measure sizes for vectors, right? Vectors, and we use norms, and that's the standard way. Today we're going to move on from vectors to matrices. How do we find matrix sizes? And there are two main, major ways to do it. One is called the Frobenius norm, and another one is called determinants. And both of them are used quite a bit in various contexts. The Frobenius norm is easy as long as you remember what the L2 norm was. The L2 norm, you basically take every single element inside the vector, and then for each element, you square it, right? So if I don't know, let's say it's 1 4 2 1, right? Then it would be 1 4 2 1, right? So that's how L2 norm works. Frobenius norm extends this idea to matrix. Instead of using every single number and putting it here, we're going to put every single number and put it here. So just an extension of the L2 norm. L2 norm is easy to get. Now, what's more important for today's lecture is the second way to kind of visualize um, the size, and that is, what if we let each column vector represent the boundaries of a shape, right? So, for example, over here, that's these two vectors. Let's say it's these two, and notice how they form kind of a boundary of a particular shape, and we want to know the area, right? So you can picture size as area as well. In this particular case, we have 3D. So we have, notice, three vectors, and we're trying to find the boundaries here. These are the boundaries, and we're trying to find the volume, right? So when we find area or volume, that is the second one we're talking about today, and that is called determinant. Determinant. Hmm. So how do we find determinant? Okay, the determinant equation, this is something you guys will have to memorize for the exam, and you need to know this for a lot of other calculations later. So for 2 by 2 is pretty easy. For 2 by 2, to calculate determinant, you basically multiply these two together like that, subtract these two together, right? So you can picture like a reverse alpha shape. So you take these two, subtract these two. So that is 2 by 2. For 3 by 3, it looks like this. You take this one, and then you multiply by the determinants here, right here. Take a second, you look, and then we take the second number, we cross out this one, so this doesn't exist, and we take the determinant of this. So notice 1, 2, we multiply by the determinant of these with the middle column canceled out. So it's plus, minus, plus. So the plus minus sign starts with plus, and then it kind of switch back and forth between plus and minus. Okay, so it's plus, minus. Now it's plus again. So the plus is right here, and that is going to multiply by the determinant of this quadrant. So this is the rules how to do 2 by 2 and 3 by 3, and it gets really uh, uh, more involved. So let's say we have a 4 by 4. So if you're trying to find 4 by 4, then what we do is the same idea. We start with plus, minus, plus, minus, right? That you always like change between them. So you once again pick this one, and then you multiply by a determinant. And then you pick this one, cancel this one out, and you find a determinant. And then the third one is this one, you cancel this one out, determinant. So you want to take a second and see if you see the pattern, right? You essentially loop through every single one here, multiply by the determinant at the bottom. And that's how it works. Okay, so you can see that for 4x4, it could get quite involved. So, okay, for now, why don't you pause the video and see if you can find a determinant and the Frobenius norm for the matrix. For the Frobenius norm, you can just leave it in this form. You don't have to actually calculate it out. All right, so pause the video. I'm going to move on. Over here is the solution. Take a moment, make sure you understand the solution. Now, finding determinants and Frobenius norm using NumPy is quite easy. In order for you to do the determinant, after you define the matrix A, you simply call determinant of A, right, in the linear algebra library. As for Frobenius norm, we just call the norm. Instead of L1, L2, we call it Fro for Frobenius, right? Frobenius norm. So you can find both pretty easily. Now, with determinants, there are some major properties that it would be nice if you know. So let's first define a triangular matrix. The triangular matrix is a matrix where one of the sides have numbers in there, and the other one has zeros. So notice the lower triangles are all zeros, right? So the numbers are only at the upper triangle. So this is the upper triangle matrix. Or this is a lower triangle matrix because the zero is at the top. So the lower part of the triangle, they have numbers, and the upper part doesn't. Or diagonal matrix, right? So these are the different kind of shapes. And with these kind of matrix, the determinants are really easy. All you do is multiply the numbers in the diagonal. Right? This drastically will speed things up for you guys on exams. So you want to make sure you know how to do that. Oh, another thing, the way we represent determinant for size is we use the absolute value symbol. The reason is because we didn't use norm is because determinants, they are not norms. They break the rules of norms. And instead, determinant is a different way of thinking about size. All right, so another interesting fact is if we have a matrix, and if we multiply the number by the matrix, let's say the matrix is n by n, right? Then this is equivalent to pulling the C out and take the nth power, right? So nth power. So it's not, you can't just pull it out. You have to pull out and take the nth power of the determinant of A. So these two are equivalent. And the third one is determinant of the product. What I mean by that is if you have the determinant of A and B multiplied together, that's equivalent to the size of determinant A times the determinant B. Okay, so these are three properties. Now I want you to pause the video again and use the three properties we just learned and see if you can quickly calculate by hand what this value is. Okay, and then you can use Python to essentially confirm your solution. So pause the video. I am going to move on. Okay, you can pause the video. This is the solution. All right, there are three other properties. So altogether, there are 6 properties. Number 4 is going to be a mystery property, which I'm not going to tell you. And then number 5 is if you have a transpose inside a determinant, you can just cancel that out. It doesn't matter having a transpose or not having a transpose. And the very last one is that determinant of a block matrix. Let's say you have an entire matrix here, entire matrix, and a matrix of zeros. If you have a shape that looks like this, it is simply the determinant of A times determinant of B. Okay? All right, now let's put all the properties together. I want you to, once again, pause the video and see if you can do all these exercises. All right, I'm going to move on. You can pause the video again. This is the solution. All right, next we're going to build on top of determinants and talk about something else different called inverse. Matrix inverse. Well, what is a matrix inverse? Previously, we kind of looked at how matrix vector multiplication, it's kind of similar to regular multiplication, right? We have analogous. If you take a vector and just multiply by 0, right, then you get a 0. Or if you take a vector, multiply by identity matrix, which just give you the vector back. And therefore, it's kind of like x multiplied by 1, right? Multiplied by 1. Other times is x can multiply by rotation and it kind of rotates it. All of these transformation allows us to almost think of x and matrix A as just numbers. So like 1, right, times some kind of number matrix. So you can think of A as a almost like a number because there's so many similarities. Well, there's another special matrix we're going to learn today, and that is called a matrix inverse. And what happens is if you have a matrix A, if you multiply by the A inverse, it's equivalent to getting an identity matrix. Remember, the identity is like kind of the matrix version of the number 1, right? So if you multiply by this, you get a 1 back. It's kind of like you have a 5, you multiply 5 by the inverse, you got a 1, right? So the matrix also has its own inverse. Every matrix might have, if they have an inverse, right? The inverse will essentially give you a 1 back. Now, if you have A inverse times A, right, it's going to equal to identity. A times A inverse is the same, right? You can flip the order, it doesn't matter. It's just like 5 times 1/5 versus like 1/5 times 5, right? So switching the order doesn't matter. All right. Now, how do we go about finding inverse? So if we know A, how do we go about finding A inverse? Well, it's actually pretty easy. If you're trying to go from A, right, to A inverse. Well, remember previously we have Ax equals to y, right? And the way we solve this is through Gaussian elimination. It turns out that you can use Gaussian elimination to find the inverse as well. So your target is an identity, right? This is what you want. You want an identity. And this is your matrix, A. So if you simply stack A and the identity here, now you perform Gaussian elimination, right? You perform Gaussian elimination until you reach the RREF. Once you reach the REF, whatever you have here on the right side is your A inverse. And that's it. That's it. This is actually really easy. If you know how to solve Gaussian elimination, you can find the inverse already. It's all just Gaussian elimination. Okay. Now, not all matrices are invertible, right? Sometimes a matrix can be inverted, other times it can't. So, for example, in this particular situation, notice how we have infinite solutions. Well, you can't invert those. So the only matrices that you can invert are the ones with unique solutions. And for the matrix that you cannot find inverse, we call those singular matrix. Okay. Now, a quick fact, tall and fat matrices, you can never invert them, right? Only square matrix can be invertible, but not always. So a square matrix that is missing an inverse, so you cannot invert it, is called a singular matrix. Right, so how do we find the inverse? Previously, I showed you that we can use Gaussian elimination. However, for the case of 2x2 matrix, there's a quicker way, so you don't have to do Gaussian elimination. The quicker way is if you have a matrix A and you want to find the inverse of A, you simply swap these two numbers. Just AD becomes DA, and then you put negative here. And after that, you divide it by the determinant of the matrix, which for 2 by 2 is AD minus BC. And that's it. This right here is the really fast equation for you to get the inverse quickly. Okay. Over here, I give you an example. When you have a chance at home, just take a quick look. All right, so now we have two matrix. You can use the 2 by 2 trick, and you can use Gaussian elimination to solve this. Pause the video and, see if you can get it. Okay, here's the solution for the 2 by 2. You can pause the video and check it out. And then here's the solution for 3 by 3. Okay? I also wrote the Python code for you guys. All right, so what is interesting is that when we find inverses, it kind of helps us solve linear systems. The way we can think of it is that, well, if we have this kind of system, right? Previously, I taught you how to use Gaussian elimination, right? Elimination. Well, instead of Gaussian elimination, another way to solve this is simply to find the A inverse. So if you find the A inverse and multiply A inverse on both the left side and the right side, notice how A inverse times A is by definition an identity. And X times identity is just itself. Therefore, we can get an expression to find X really, really quickly. Right. So this right here, by knowing A inverse, it can help us solve this type of problem. And okay, so over here, the way we can solve this with inverse is in Python, it's called IMV for inverse. Okay. So that's what you want to use. All right, so let's pause the video again and do a quick example. See if you can find the inverse of A and try to solve this problem right here. Okay, pause the video. I'm going to continue. Here's the solution. All right, so now we can go back to that original question I was asking, the psychological problem. Well, let's say we design the question to kind of reveal certain dominant feelings that you have. Okay, so right here it says that what we are saying is that each person can have three possible feelings. I mean, in more complicated situation, you can have way more than three. But let's just say for this situation, there are three feelings, and we want to know which one this person feels more, okay, from time to time. And so X1 is anxiety, X2 is resilience, X3 is attention. And then we're going to set it up. So first question, when unexpected stress arises, I feel overwhelmed and have difficulty stay calm even if I usually recover well. So this right here is kind of saying that, okay, it talks about if this is true for you, then it's kind of demonstrating anxiety. So we give it a high score. Now, if you're the designer, you're the psychologist, you have to design the number. So we give it a high score. So whatever the person's score was, like this was the score that you labeled, if you have a high anxiety, this number will be high. So we give it a high score, and then it kind of shows a negative resilience where you are kind of having difficulty. And then you are showing that you are kind of paying attention to it. So therefore, the first equation, it's saying that the combination of this then leads to whatever score that you gave. And the second question, after a stressful event, I'm able to bounce back, right? So that's a bit about resilience. So it's showing resilience, right? It's showing resilience, and it's showing a little bit of anxiety, right? Like anxiety still plays a role, right? So this question, if you answer a high number, it's essentially saying that there's a bit of anxiety, but you are doing okay. And the third question is attention. When working on demand task, I can stay focused, right? So this is attention. So this is a high attention, X3, right? Attention. And I can handle pressure. So it's resilience. So it's resilience and attention. So if you score high on this one, it kind of says you're more like that. So these equations are designed by like people that make studies. So they come up with these questions, and then with these questions, they'll people like specialists. After you've had a lot of experience, you say, "Well, I think the score will be can be constructed this way." Right? We make it up basically. We make it up to the best of our knowledge. It's not exact science, but anyways, this is basically you understand the general idea of why certain questions anxiety score higher or lower. So, anyways, you notice how now we have three equations, right? And then the numbers 3, -1, 1 can be placed into a matrix. So whatever you are truly feeling, so whatever you're truly feeling, X times by A will be is results in the score that you gave. All right, so let's look at Professor Wu's response. So let's say for me, I score 135. Okay, so therefore we can solve like 135 is my Y, right? And then we knew the A, and we can now essentially solve for X, which reveals to you my hidden dominant feeling. Okay, so like I told you, we can solve this with Gaussian elimination, or we can just multiply by A inverse, which is what I'm going to do. So I'll take my score, 135, right? 135. I'm just going to multiply by A inverse, inverse. And then it says that, okay, so these are the scores, which means that, okay, so what were the three? The first one was anxiety. So it says some anxiety, it's there, but it's not really dominant, right? It's not that large. Whereas my resilience is pretty big number. And this is a typo. That's supposed to be attention. And attention is supposed to be high. So I'm good at paying attention, and it's saying that I'm pretty resilient. And I have some anxiety, but not like taking over my life. Okay, so this right here, by answering the question, we can collect the data and essentially reverse engineer how I was like with the dominant feelings that I have with numbers, right? So what is interesting here is I didn't solve this use Gaussian elimination. I find A inverse. And then once I find A inverse, right? So this is some kind of fixed number we already know, and we just kind of multiply our score by A, and we get the solution back. And this is actually a better way, right? You can imagine if we don't know the A inverse, every time you get somebody's score, you like every single person's score, you need to solve a Gaussian elimination over and over and over again. And you don't want to do that. Like ideally, you just find the A inverse, and then whoever score you get, you can just kind of multiply over here. So having an inverse like really speeds things up in this case, and it avoids like the whole process of Gaussian elimination, right? Well, at this point, I want you to pause the video. You have your numbers. You have your three numbers. Use Python and see if you can multiply by the inverse, and then you can figure out based on your answer what your dominant feelings are. Okay. So that's it for that. All right. You pause the video so you can do this exercise. We're going to move on. Now that we understand the concept of inverses, there are also inverse properties that you need to know. So one of the inverse property is that uniqueness. That means if there is a invertible matrix A, like if you can invert it, you have A1 and that's it. You're not going to have multiple inverses that does the same thing. It's unique. That's what that means. And the inverse of product. If you have two matrices multiplied together and you take the inverse, it's kind of like the transpose. You just flip the order of two of them, and then you put inverse on each one individually. Another one is transpose. So if you have a transpose with an inverse, guess what? You can just flip them, and they're equivalent. Like it could be inside, it could be outside. It doesn't matter. Another thing is multiply by number. So here's a matrix, here's a number. And if you're if you take the inverse of this, you simply move this number outside like this, 1 over c, and then you move the inverse here. Okay, so these three properties are pretty useful, and we're gonna do a quick property exercise. Now pause the video and see if you can solve these problems. Right, you can use Python for this. Okay, pause the video. I'm going to continue. Here's the Python code to help you if you're stuck writing this code. All right, now there are lots of properties. So we did the first three. Let's look at another three. Well, in this property, it says that if you have a diagonal matrix. Now remember, diagonal matrix is a matrix with only diagonal elements and everything else 0. These are very easy to find the inverse because instead of solving for the inverse, you just find the inverse of every element at the diagonal. So previously that was D1, right? So that was D1. It just becomes 1 over D1. So it doesn't get easier than this. So you want to remember this property. If you end up doing this on an exam and you try to use Gaussian elimination, it will take you a long time. Another thing is block matrix inverse. So right here, right, this is a diagonal, but a block matrix, right? So this is a matrix of non-zero, matrix of non-zeros. Now you want to, and then the diagonal, that's a matrix of zeros, matrix of zeros. So in those cases, if you want to find the matrix of the inverse of this matrix, all you have to do is find the inverse. So you can split them into smaller problems that is more digestible, right? It's much easier to solve the inverse of A and D. Okay. And this one, Shor's complement, yeah, you can take a look. We do use it in machine learning, but for now, like this essentially help you find the inverse of anything. But it's quite a bit of work. So just put it somewhere in your head that you can take inverses of a square matrix, and you can speed it up. But we don't really need to get too much into detail on this. The next property is that if you have a determinant of an inverse, well, that's easy. You just take the 1 over the determinant, right? This is a pretty easy property. And then this one, well, it's saying determinant of an identity. If you have it, is always 1. All right. So the size of a 1 box, the volume of a 1 by 1 by 1 box is 1. That's basically what this is saying. And the very last one is determinant of an inverse. So, well, determinant of inverse, well, we did that before. Basically saying that we can just find determinant A, determinant B, and then take the inverse of that. So this is all these are pretty easy. Okay, so that's it for today. Let's put everything you learned today together by solving these problems. Give it a try. Like this right here, by the way, is a symbol for normalization, okay? This is a vector that's normalized, which give you a review. We did this a while ago. So a normalized vector is a vector of length 1, okay? So when you're solving this, you want to make sure you remember that. So pause the video, try to do these exercises, and then I'll show you guys the solution as well. Okay, this is a question to solution 1, solution 2, okay, solution 3, solution 4, 5, and 6, solution 7. I mean, you have access to the slides, so you can basically and look at it. But for the people who is too lazy to look at the slides, you can just pause it. And that's it for today. I did provide extra practice questions. So if you want to get more practice, these are some extra practice for finding inverse. And here's the solution. Okay. Here is more solution. Over here is another problem. Solve linear system. Pause the video if you want to solve it. And over here is the solution. And I think that's it for today. Yep. Have a good one.